Okay, we now embark on the third melody, symmetry. Symmetry had a long history in human civilizations. So I shall talk about first the origin, then the Greeks, then Copernicus and Kepler, then 19th century, and lastly the 20th century. About the origin of the concept of symmetry, it's obvious that the symmetry is a very old concept in all human civilizations. How did it come about is a subject which has been speculated upon, but with no firm conclusions. We could imagine that the early man had observed many natural symmetries from such beautiful phenomena like the rainbow, or the beautiful complexity of the snowflakes, or the symmetry of the beautiful marine creatures. This was a sketch made by a 19th century marine biologist. You see that the different microbes had a very complicated symmetry. For example, the top right one has a perfect octahedral symmetry. The bottom right one has octahedral, has a dodecahedral symmetry, beautiful ones. We could imagine that from these early phenomenological observations of symmetries, mankind gradually absorbed the idea of symmetry, and its influence creeps into many areas of human activities, including paintings, sculptures, music, literature, and architecture. For example, this is a beautiful gu from Shang Dynasty. Shang Dynasty 3,500 years ago, as you know, was famous for the bronze culture. That was unique in all ancient civilizations. And if you look at the beautiful symmetry of this piece, you cannot fail to be impressed by the aesthetic feelings of the early sculptor. This is a photograph of a window in a mosque in Spain. You know, Spain was controlled by Islamic civilization for many centuries, and during that the Islamic architects built many mosques. This is one of them. The Islamic architectural styles are distinguished by their use of the concept of symmetry. I will have the occasion to come back to this picture later. These two conches are kept in the Gugong Boguan in Taiwan, because during the Qing Dynasty, people found that most of the conches are of the type on the right, but occasionally, very occasionally, there were ones which has the left-handed spiral, and they thought that if you have one of these left-handed ones on your ship, you would survive in any big storms. So therefore they decorated the left-handed one in this very complicated decoration, and it's now kept in the museum in Taiwan. Here's a poem written by Su Dongpo. This poem has the peculiar property that if you read it forward, it reads like 潮水暗浪雪山泉 元谱宇宙调月明 etc. etc. ending with 碧峰千点树欧青. But the poem can be also read backwards. starting from the lower left corner, 青鸥数点千峰碧，水接云山四望遥, etc., etc., ending with 群山雪浪暗随潮. Now you might say that this must be because Su Dongpo did not have anything to do, so he composed this very peculiar poem. Now let's look at this. This is a violin duet by Bach, and it was 2 pieces of violin. If you look at the music of the first piece, if you look at the music of the first piece, it goes this way, and it ends here. Now if you reverse this, going back this way, that is precisely this second piece. So this is even more difficult to compose than Su Dongpo's poem, because at every moment the 2 pieces of music must harmonize with each other. What both of these 2 exercises in literature and in music show that the early scholars were well aware of the importance of the concept of symmetry in literature and in music. Starting from these early appreciations, when we go to the Greeks, we found that the Greeks were very much obsessed with the concept of symmetry. They discovered these 5 so-called Platonic solids. They were actually discovered before Plato, but now it goes by the name of Platonic solids. And these are from the upper left, the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. Each has maximum symmetry. And the amazing thing is that the Greeks proved not only that they found these 5 maximally symmetrical solids, they proved that there were no others, that any other 3-dimensional solid would have less symmetry than these 5. In fact, there is a theory that the reason that Euclid wrote the Elements was because he wanted to formalize the proof of the theorem that there are only these 5 most symmetrical solids. Whether that is true or not is unclear, but the theorem which states that these 5 are the only 5 maximally symmetrical solids was one of the last theorems in Euclid's book. The Greeks were so obsessed with the concept of symmetry. They were so obsessed with the beauty of the concept of symmetry that they thought everything under the sun must be made because of the concept of symmetry. So there was born the idea of the harmony of the spheres and the dogma of the circles, meaning that everything fundamentally must be very, very symmetrical. And they applied these ideas, the harmony of the spheres and the dogma of the circles, to astronomy. They first say that everything has to be circular. When they found that not everything was circular, for example, orbits were not exactly circular, they made it into a circle on a circle. If you have a small circle going around a big circle, and when that doesn't work, they make it a circle on a circle on a circle. And that was the general direction of trying to maximize the use of the concept of symmetry in the structure of the universe. We know that that was a futile attempt. In fact, that attempt, that general direction, set back the progress of astronomy for almost 2,000 years. What started the astronomers to come out of that complicated but wrong direction of astronomy started by the Greeks was what happened to Copernicus and Kepler. At Kepler's time, at Copernicus and Kepler's time, there were known 6 planets: Saturn, Jupiter, Mars, Earth, Venus, Mercury. And their orbits were thought to be circular. And it was thought that the diameters of the orbits of these 6 planets were more or less known. So there was a question of why were there only 6, and why did they have orbits which had the observed diameter ratios. And a young astronomer, Kepler, in 1596 wrote a book called Mysterium Cosmographicum. That was the beginning of the career of Kepler as an astronomer. In that first book, he invented an idea of why there are 6 planets and what were the ratios of the diameters of the 6 planets. He said that there are 5 regular solids and we have 6 planets. So the idea is that he took the biggest planet to be a sphere in this diagram. And inside of this big sphere, which is Saturn, he put a cube, one of the 5 solids, so that the 8 corners of the cube touch the sphere. And inside of this cube, he put the next sphere tangent to this cube, and that he thinks is Jupiter. And inside of that sphere, he put the next regular solid, which is the tetrahedron, etc., etc. So he has 6 spheres. In between them, there are 5 solids. And of course, there is a possibility of changing the order of the 5 solids. Here, he took the order to be, the biggest one is cube, next one is icosahedron, next one is the dodecahedron, and so on and so forth. But of course, there are 5, there's a permutation of the 5 objects, so there are 120 possibilities, and he tried all of them. And he found that this one is gives the best approximation to the ratios of the diameters of the 6 planets, of the 6 planetary orbits. And so he wrote this book. Now we know that this is totally wrong, because in the first place, we know there are more than 6 planets, and there are only 5 solids. But we must realize that the method he used is very much exactly the same thing that we are doing today. One of the methods now to find reasons of some observed regularity is A, choose some mathematical regularity resulting from symmetry requirements, like the 5 solids. B, match it to observe the regularity. And this is very much what exactly is being done, especially in the 1940s, 50s, and 60s about elementary particle physics. We observed many new particles, and they had observed the regularities, they had observed symmetries, and we try to match those observed symmetries with some mathematical symmetries. So the idea that Kepler used is still very much alive today. Kepler was a person who was very interested in geometry. This is a page from one of his books, and many of the ideas that he explored are in modern mathematical language, very important. For example, there's concept of duality. According to the duality, the cube and the octahedron are duals of each other, because if you take the cube and take the center, the cube has 6 faces. Each face has a center. So the 6 centers of the cube, if you think about it, that forms an icosahedron. And the icosahedron has octahedron. The octahedron has 8 faces. Each face is a triangle. Each face has a center. And so there are 8 centers for this octahedron. And if you look at it, that 8 centers form exactly a cube. So Kepler arrived at the idea that these 2 solids are duals of each other. This is self-dual. These 2 are duals of each other. So that's one of the geometrical concepts. And he also had the idea of tiling. Tiling is an idea which we'll come to later in greater detail. And in his book, he had all these arguments and concepts. In particular, he discussed why snowflakes are 6-sided. That snowflakes are 6-sided in the West was first appeared in this book, Albertus Magnus, in the year 1260. But it was known in China already in 135 BC. It's some 13 centuries earlier than in the West. The original discovery is no longer in published books, but in the Taiping Yunnan of Song Dynasty, you read this page. It says, 凡草木花多5处，学花多6处. So this is the first statement in Chinese literature that snowflakes are 6-sided. And this is attributed by the Song book to Han Shi Wai Zhuan. Han Shi Wai Zhuan was in Xihan. So it was 13 centuries before the Western discovery. However, there's a difference. In the Chinese civilization, this phenomena observed, but people did not explore why. What's different with Kepler was that he observed that the snowflakes are 6-sided, and then he asked why. He wrote books about it. Now, if you read the books are very interesting. They did not really hit on the right explanation, but nevertheless, the effort that Kepler devoted to exploring the reasons behind this phenomena was absent in Chinese civilization. And that's perhaps one of the reasons why natural science did not originate in China. Now we come to the 19th century. And in the 19th century, the concept of symmetry became much more important in physics because of the study mathematically of groups and physics-wise of crystals. In the year 1832, Galois died in a duel. In those days, in Europe, people had the system of, instead of quarreling, having duels with each other. And he died in one of these stupid duels. He was only 20 years old. And but before he died, he quickly wrote down his main ideas. And those ideas made mathematicians at that time realize that the concept of group, which was before Galois, was very powerful, because he used that to investigate a question which was already investigated by the Greeks, but without solution, namely whether one can find a formula for finding the roots of higher degree polynomial equations. And after Galois, it became clear to the mathematicians that the concept of groups is very important. And so in the 19th century, the concept of groups was greatly developed, and with Sophus Lee adding continuous group to it, and in the 20th century, we now find that the concept of groups occupies a central place both in modern mathematics and in modern physics. The concept of group is the mathematical representation of the concept of symmetry, and I shall try to explain this. Symmetry and invariance are deeply related concepts. Let us take these 5 solids. For example, let's take the cube. The cube has many invariant operations, meaning if I take this cube and if I take a central vertical axis and I rotate this cube by 90 degrees around that axis, it goes back to itself. So one says that that cube is invariant under a 90-degree rotation around the central axis. It's clear that if I make an axis going through these 2 points, if I rotate the cube around that axis by 120 degrees, it will be invariant. It will come back to itself. So that cube has many rotational invariant elements. And the collection of all those rotational invariant elements form a group. And that group is the rotational invariant group of this cube. So the concept of invariance and the concept of symmetry are deeply related. When the physicists in the 19th century began to study crystals, they tried to classify crystals. Then they found that crystals has many symmetries. So let us give an example. In graph A, on the left, you have a lattice. We imagine this lattice to be extended in all directions, right and left, up and down, to infinity. And that is a big lattice with a lot of symmetry. Lattice B on the right is similar to it, but it is decorated with a lot of alphabets D in various orientations. Also, we imagine this to be extended in all 4 directions to fill the whole space. Now we want to go to a discussion of the symmetry of A. Now, A clearly has many translational symmetry. If I take this lattice and displace it by 1 unit to the right, or 5 units to the right, or 3 units up, it goes back to itself. So this lattice is invariant under a displacement by 3 units to the right, etc., etc. So it has lots of displacement invariance. But it also has rotational invariance. If I take this lattice and rotate it around this point by 90 degrees, it goes back to itself. So a rotation around this point by 90 degrees is an invariant element of this diagram. Of course, a rotation around this point by 90 degrees is also an invariant element. A rotation by 90 degrees is called a fourfold rotation. Fourfold because that's 360 degrees divided by 4. So how many fourfold symmetries does this lattice have? A 90-degree rotation is called a fourfold rotation. It will be denoted by 4. It is an invariant element of the graph. So we have all these. We have the rotation around each of this by 90 degrees is an invariant element. So There's a four-fold symmetry, four-fold symmetry here. But there is also, this is also a four-fold symmetry point. So if you add that, you'll find that these 9 were the original ones that I drew, but these additional ones are the four-fold symmetry around these points. But you then look at it and you find that there are other symmetries. You can rotate around this point by 180 degrees. So this point is a two-fold symmetry. This point is a two-fold symmetry. This point is a two-fold symmetry. If you add all those, you get this diagram. So the structure of the four-fold and two-fold symmetries of this diagram are like this. But that's not all, because you can also make reflections. If I make a reflection around this line, it's an invariant element. If I make a reflection around this line, it's also invariant. So I drew these lines. These are the reflection invariance lines. And this collection of two-fold symmetry, four-fold symmetry, and these reflection symmetries, together with the displacement symmetries, form the invariant group of symmetries of this diagram. To explain this more clearly, let us now look at this one. This one, as I said, was the same as the original one, except it's decorated with these. And if you think about it, it's clear that all the four-fold symmetries of the original diagram are still four-fold symmetries. All the two-fold symmetries are still two-fold symmetries. Because when you rotate this figure, it can become this one, become this one, this one. The only symmetry that's absent in this one, compared with the earlier one, are the reflection symmetries. Because if you reflect this diagram, no matter around what axis, the alphabets D become B, but there are no B's in this. So therefore, the reflections are not invariant elements. And so therefore, the invariant group of this does not have all those symmetry lines. So this diagram has a symmetry group which is smaller than the previous diagram. So you see that what we have been doing is we analyze the concept of symmetry through defining it more precisely by its invariant group. Now the amazing thing is that in the 19th century, in 1891, the mathematicians and the physicists arrived at the conclusion that in 2 dimensions there are only 17 different space groups. And that's the 17 are exhibited here. This one, if you look at it more carefully, it has exactly the same symmetry as what we had talked about as A. This one has exactly the same symmetry as what we talked about as B. You see, this one you cannot reflect, because if you reflected these little triangles go into the other shape which is absent in here. So this is the symmetry. This has the symmetry of A. This has a symmetry of B. And there are other symmetries. This one, for example, has a 6-fold symmetry around this point. This one has a 3-fold symmetry, and so on and so forth. And so there are 17. If you go back to your bathroom and look at your bathroom floor, you'll find that your bathroom floor has the symmetry of one of these 16. But the amazing thing is that in 1891 they proved that there are only these 17. It's easy for you, after you look at it for a while, to realize that these 17 symmetries are all different. It is a much more difficult thing to prove that there are only these 17. That you cannot have another diagram which has the displacement symmetry forming a lattice, which has a different rotational displacement combination of a symmetry group, which is different from one of these 17. The history of how this was found is very interesting. It was first found that in 3 dimensions there were 230. Why first in 3 dimensions? Because it was motivated by physics. Physicists wanted to classify crystals, and everybody knew that crystals had some displacement symmetry. But then rapidly physicists understood that there are other symmetries, and the property of a crystal is very much determined first by its symmetry. So they began to classify the symmetries of crystals, and this work was done on the side of physics by physicists, and on the side of mathematics by mathematicians. They proceeded independently, and for a long time there was great argument about whether there were 230 or 229. But eventually, in the year 1890, they settled through different methods that there are 230 crystal classes. After that, Fedorov, who was a crystallographer of Tsarist Russia, said that, of course, we could do this also in 2 dimensions. So he published a paper the next year and said that in 2 dimensions there were 17. Now, this was in the last year of the 19th century. Then you probably all know that in 1900, David Hilbert, perhaps the greatest mathematician around the time, made a speech in which he announced 23 problems for the 20th century. These are the well-known 23 Hilbert problems. One of these Hilbert problems was precisely the following. Okay, in 2 dimensions there are 17 space groups. Each of those symmetries is called a space group. In 3 dimensions there are 230 space groups. Is there a finite number of symmetries in higher dimensions? That was one of the Hilbert problems. That problem was quickly solved within some 7 years by a German physicist named Bieberbach, who proved that the answer is yes. In any higher dimension, there are only a finite number of space groups. So that's an existence theorem. But the next question is, how many in 4 dimensions? And that becomes very complicated because we do not have 4-dimensional geometry in our head. And finally, with the computer, around there was a great dispute about the numbers, but around 1970, it finally settled down to this number, 4895 different space groups in 4 dimensions. Higher dimensions is still open. There are upper bounds and lower bounds to all dimensions, but the precise number is not known. Probably with the modern computer, one will be able to figure out at least for 5 dimensions, but that's a very specialized subject. I had earlier shown you a photograph of a window of a mosque in Spain, and the bottom part of that, if you look at this one, if you look at this and repeat it both this way and this way, you'll see that that has exactly the same symmetry as figure A that we had discussed in detail before. This is a very intricate symmetry, and it has a 6-fold symmetry. A few years ago, somebody wrote a book. He went to various mosques of the Islamic religion from many places and photographed the windows and the walls, and then wrote a book saying that all 17 2-dimensional space groups had been realized in some of the decorations in Islamic architecture. Now we come to the 20th century. In the 20th century, symmetry became a fundamental concept. Although symmetry was very useful to the mathematicians in the 19th century, to the physicists in the 19th century, as I just outlined, it was in the 20th century that that symmetry became fundamental in physics. I will discuss this importance of symmetry in physics in 4 subsections: Lorentz symmetry, then general relativity, then symmetry in quantum mechanics, then gauge symmetry. We all know that special relativity was ushered in by Albert Einstein in the year 1905. Before that, already 20 years before that, in 1881, and then later on in a more accurate experiment in 1887, Michelson and Morley tried to measure the movement of Earth relative to ether, because everybody thought that Maxwell's waves propagate in a medium, and that medium was called ether. And so Michelson and Morley tried to measure that relative velocity of the Earth in ether, and they could not find it. And what Einstein special relativity did was to have solved that puzzle, namely there was no ether. We would ask, how did Einstein, a 26-year-old patent of his clerk, launch into such a revolutionary idea? We find that, in fact, his interest in the subject started very early. In 1899, when he was just about 20, he wrote a letter to his girlfriend, who later became his wife. And in the letter he said, "I returned the Helmholtz volume, and I'm now rereading Hertz's propagation of electric force with great care, because I didn't understand Helmholtz's treatise on the principle of least action in electrodynamics. I'm convinced more and more that the electrodynamics of moving bodies as it is presented today doesn't correspond to reality, and that it will be possible to present it in a simpler way." This shows very clearly that as a student, Einstein had the taste to focus on the most important problems of physics. He mentioned here about the electrodynamics of moving bodies. He mentioned here the principle of least action. These were the core of the foundation problems of physics. And as a young person, he focused on these. That was perhaps one of the reasons of his later great success, that he was able to seize on what was the most important. Now the statement, the name relativity was not invented by Einstein. Poincaré, 1 year before, 1905, namely in 1904, in a lecture he gave in St. Louis, which is now published in a book called Physics for a New Century. In that book, in that article, read in 1904, 1 year before Einstein's special relativity, there is a remarkable paragraph. Let's read this paragraph very carefully. This is a paragraph by Poincaré. "The principle of relativity, according to which the laws of physical phenomena should be the same, whether for an observer fixed or for an observer carried along in a uniform movement of translation, so that we have not and could not have any means of discerning whether or not we are carried along in such a motion." This was one paragraph of that speech. If you think about it, this paragraph is exactly right. it states the spirit, the soul of the concept of special relativity in a very concise way. Every word in this is correct. But if you read his lecture, the latter part of his lecture, you realize that he did not understand this paragraph. That Poincaré had this philosophy correctly, but he did not know how to materialize that into physics. But later paragraphs show that Poincaré did not understand how to interpret this philosophy. He did not question the concept of absolute time. The thing that he failed in was whether time is absolute, whether my time and your time and his time are exactly the same. Now, the fact that the perception that there's an absolute time is with all of us, is with all the children, because the children learn that everybody has the same time. So that became a fixation, and that fixation was the thing that Poincaré could not break away from. And Einstein had the insight to break away from that. So that is called the relativity of simultaneity. Simultaneity means equal timeness. And Einstein was the one who realized that all the problems around that time would be resolved if you propose simultaneity is not an absolute concept. It's a relative concept. And that was a revolutionary concept that Poincaré did not see so. Now, Lorentz was a towering theoretical physicist around that time, and he also was dealing with this problem. And in fact, it was he who wrote down these equations, which I know you are very familiar with. These, in fact, are called Lorentz transformations. Lorentz wrote down these equations so that the transformation from x, y, z, t to x prime, y prime, z prime, t prime was not written down by Einstein. It was first written down by Lorentz before Einstein, and that is the name that we still have for these transformations, the Lorentz transformation. But Lorentz did not understand that this t prime is just the time of the traveler. How do we know this? Because 10 years afterwards, he wrote, "The chief cause of my failure was my clinging to the idea that only the variable t can be considered as the true time, and that my local time t prime must be regarded as no more than an auxiliary mathematical quantity." So that was Lorentz's failure. So therefore, if you look at that period, you would say that Lorentz had the mathematics, Poincaré had the philosophy, but Einstein had the physics. Is that today we always say that the one who created special relativity was Einstein. Was that fair to Poincaré? Was that fair to Lorentz? Let us read this article by Whitehead, a great philosopher. He said, "To come very near to a true theory and to grasp its precise application are two very different things, as the history of science teaches us. Everything of importance has been said before by somebody who did not discover it." This is a very correct statement, and there are many, many examples, more than the example in special relativity that I just outlined for you. When Einstein wrote his paper in 1905, he did not have the word symmetry in mind. Throughout the article, the word symmetry did not appear, nor did he feel that what he did had anything to do with symmetry. But in 1907 and 1908, Minkowski, who was a great mathematician, pointed that out, that what Einstein did, mathematically says that there is a symmetry group of physical laws. When Einstein first read about this work of Minkowski's, he did not like it. He called it superfluous learnedness. Superfluous learnedness means it's very learned, it's 好像很深 but superfluous, 没什么多大用处的. So the first reaction of Einstein was that yes, there is this symmetry, so what? It's uninteresting. But he quickly learned that that is not the case. How do we know? Because next came general relativity, which was published in 1915 and 1916. And the origin of general relativity was described by Einstein in his old age. Einstein, in his 70s, said, the basic demand of the special theory of relativity, that is, invariance of the laws under Lorentz transformations, is too narrow. That is, that an invariance of the laws must be postulated also relative to nonlinear transformations of the coordinates in the four-dimensional continuum. This happened in 1908. So what he is saying in his old age is that in 1908 he realized not only that the symmetry pointed out by Poincaré, by Minkowski was important, that it is not enough. He wanted to have more symmetry. And that more symmetry was the requirement that the equations must be invariant not only under linear transformations, but under arbitrary transformations. He called nonlinear transformations. And that spirit, that mathematical spirit, was what made him try to write a set of equations that has that invariance property. And that's how special relativity, general relativity was created. Of course, in that long struggle of about 8 years, he also had the aid of physics. The physics was the equivalence principle. So you might say the physics principle of the physics equivalence principle and the mathematics of greater symmetry were the two legs upon which Einstein built general relativity. I had said recently when I was asked to talk about Einstein's work, I said, as a scientific revolution, general relativity is unique in the history of mankind. The grandeur of its conception, its beauty, its sweeping scope, its spawning the awesome science of cosmology, and the fact that it was conceived and executed by one single person reminds me of the act of creation in the Old Testament. And I wonder whether Einstein himself had thought of this comparison. Although I put that last sentence in parentheses, I think I not only wonder, I'm sure Einstein himself had thought of this comparison, namely that his creation of general relativity was like God's creation of the universe. This is a picture of Einstein in his house in Berlin. He went to Berlin in 1913 and he spent 20 years there. In 1933 he left Berlin for the United States, and he never returned to Europe after he moved to Princeton. Next subsection, symmetry in quantum mechanics. So what we said before in the last half an hour is that at the beginning of the 20th century, because of special theory of relativity and general theory of relativity, symmetry was very much an important concept in theoretical physics. Now we come to quantum mechanics and symmetry. With Bohr's 1913 theory of the atom, quantum numbers, spin and parity, come very much into the picture, both for theoretical reasons and experimental reasons. In Bohr's theory, there was the quantum number n. Additional quantum numbers L and M were soon found necessary. They were found necessary both because there are additional degrees of freedom, because the Bohr's theory was a two-dimensional one, but actually the atom is a three-dimensional one. So you need two more dimensions, and each dimension should give you one more quantum number. So it was already realized after 1913 that beyond n there are additional quantum numbers, and these were matched with experimental data, so it was known there need to be three quantum numbers, n, l, and m. And soon after that, experiments showed the existence of additional degree of freedom, which Uhlenbeck and Gaussman identified as spin. This fourth degree of freedom is the spin. In 1924, Laporte was a physicist in Europe. He later moved to the United States and became a professor in the University of Michigan. When I visited Michigan, he was still living. He experimentally discovered that the energy levels of complex atoms are of two types, even and odd. So he formulated Laporte's rule. The rule says that in emitting a photon, an even level always goes to an odd one, and an odd level always goes to an even one. And this is true not just for the simple atoms, but for any atom. And this was called Laporte's rule. And for a long time it was not clear what is the origin of this rule. These behaving quantum numbers and rules were finally understood after quantum mechanics was developed as consequences of symmetry through the use of group theory. And that was in particular ushered in by Wigner and by Hermann Weyl between the years 1927 and 1930. An example of that was Laporte's rule was due to reflection invariance. Because electromagnetic field has reflection invariance, Maxwell's equations is reflection invariant, and therefore reflection symmetry is inherent in an atom. And because of the difference of behavior under reflection, there occurs a concept called parity. And parity, even or odd, explains the evenness and oddness of Laporte's rule. In the 1930s, the application of group theory to atomic and molecular physics were extremely successful. Physicists at first resisted the introduction of group theory, a new kind of math. This is very much like Einstein's original resistance at accepting the usefulness of the concept of symmetry introduced by Minkowski. There was, in fact, around 1930, the term group pest. Pest means 害虫. Group pest means it's something that you don't like and you want to discard. In fact, there was a famous theoretical physicist named Slater. He was a very active and very productive theoretical physicist in the late 20s and early 30s. He was for a long time chairman of the physics department of MIT, and he built up the MIT physics department. I had met him. He was perhaps 25 years older than myself, and he didn't like the group theory. This is mostly because group theory is a new math, and if you have not learned this new math, you try to say that it's not so useful, I can do it without it. So he tried to do atomic theory without group theory. And one day he found that the determinantal wave function is antisymmetrical. At that time, the symmetry of the wave function became important, and that was deeply involved with group theory, and he didn't like that. But then he found that the determinants are antisymmetrical automatically. So he did not have group theory. He can have antisymmetry built into his theory automatically. So he said, he wrote to his friend, I have slaughtered the group test. But of course, very soon it turned out that he didn't slaughter it, because the antisymmetrical wave function is not just a determinant. It could be a summation of determinants, and that itself cannot be rewritten as one determinant. So after a number of years of struggle, group theory was here to stay. By the mid-1930s, students had to learn group theory. When I went to Chicago as a graduate student in 1946, the department had the physics department had the group theory courses for physicists. And of course, when I became a postdoc in the 1950s, group theory became very important, not only in atomic and molecular physics, but also in nuclear physics, and with such things like Rockout coefficients and 6J and 9J symbols. By the mid-1950s, all theory graduate students had to learn a lot of group theory. In 1957, I drew this diagram. Symmetry and invariance are deeply related concepts. On the left side, on the lower left corner, I have a box saying other consequences. That includes, say, symmetry as applied to crystal physics. But the main use of symmetry in physics by the 1950s had shifted to the central line, conservation laws. Conservation laws are very old. In fact, conservation laws are older than Newton. But it was only in the 20th century that the existence of conservation laws become related to the concept of symmetry. The conservation of linear momentum was shown in 1918 to be deeply related to the concept of displacement invariant of physical laws. The concept of angular momentum conservation, which was very old, was related to rotational invariance of the physical laws. So the relationship between conservation laws and symmetry was realized only in the 20th century. For discrete symmetry in classical mechanics, there is no such relation. But in quantum mechanics, discrete symmetry also generates conservation laws, like parity. And with conservation laws, of course, there come such things like quantum numbers and selection rules. So this was the diagram showing the importance of the concept of symmetry in physics, drawn up in 1957. I want to make several remarks about this diagram. First, conservation laws were known before Newton, but their relationship with symmetry was understood only in the 20th century. Second, the Schrödinger equation is linear in psi. Thus, there's the superposition principle. If you have a linear Schrödinger equation, you can superpose wave functions. And that superposition the Schrödinger equation is linear in psi. Thus, there is the superposition principle. Hence, the symmetry of an elliptical orbit can be described in the same way as that of a circular orbit. A circular orbit has more symmetry classically than an elliptical orbit. But in quantum mechanics, an elliptical orbit, like a p-wave, you have, when you rotate the p wave, you get 3 wave functions. But the 3 wave functions can combine. So the symmetry of the p waves, in some sense, is put onto the same grounds as the symmetry of the s waves. In other words, elliptical orbits also has rotational symmetry in quantum mechanics, while it does not seem to have rotational symmetry in classical mechanics. Hence, the symmetry of an elliptical orbit can be described in the same way as that of a circular orbit because of the superposition principle. That is why symmetry plays a much greater role in quantum mechanics than in classical mechanics. After World War II, particle physics took center stage because of the discoveries in cosmic rays first of new particles, and later the study of these new particles in accelerators. And in the 1950s, the main research topic were the new particles and their quantum numbers. New symmetries were found. Thus new larger groups were introduced. Here we must first talk about discrete groups and Lie groups. The lattice that we were talking about, the symmetry of the crystals, those symmetry elements were discrete, individual ones. They were separate. Discrete groups are very interesting and has very interesting structures. But in the 19th century, Sophus Lie of Norway introduced the idea of Lie groups, continuous groups. If you rotate around a point, you can rotate by any angle theta. Theta goes from 0 to 2 pi. So that becomes a continuous group. Continuous group was originally introduced by Sophus Lie to study transformations. But by the 20th century, it has become a most important concept in mathematics and in physics. The 3-dimensional rotation group is called SO3. SO3 means it's all the 3 by 3 real orthogonal matrices with determinant 1. And orthogonal means that A and A tilde multiplied is equal to 1. So this slide shows the definition of SO3. It's the collection of matrices. When these matrices multiply on each other, they of course give you another matrix satisfying the same property, so it forms a group. You can also talk about an SO31. SO31 is a 4 by 4 real matrix which satisfies this property. And that's the Lorentz group. Maxwell's equations are invariant under this group. By the 1950s, people began to talk about SU2, SU3, etc., etc. Now, I will give you some examples of the importance of group theory. First example is the periodic table. This is a familiar periodic table. It was drawn up, the idea, it's a brilliant idea due to Mendeleev in the 19th century, in which he put the different known elements into columns with similar chemical properties. At that time, there were many holes in the table because there were many elements which were not yet discovered. So by the early 20th century, it became clear that the periodic table was a very useful, very important concept. But it has these periods, 2, 8, 18, and it was not known at first what was the origin of these numbers, 2, 8, 18. It turned out they are related to the representation of the group SO3. SO3 is the 3-dimensional rotational group. It has the representations. The representations have sizes of 1 by 1, 3 by 3, 5 by 5. These numbers are related to the structure of the periodic table. The periods 2, 8, and 18 are in fact 2 times 1, 2 times 1 plus 3, 2 times 1 plus 3 plus 5. These numbers 1, 3, 5 are the dimensions of the representation of SO3. So you show that the intrinsic structure of the elements and their chemical properties are in fact deeply related to group theory. Next example, why there is spin 1/2. Dirac in 1928, in trying to make a relativistic theory of the electron, launched a great revolution. Mathematically, he created the idea of the Dirac operator related to the representation of the group SO31. Physically, at one stroke, he explained 3 striking things. He explained why there is spin 1/2. Spin 1/2, I had said earlier, was first introduced. There was a quantum number that was found, in fact, by Heisenberg, by groping around, by sort of ad hoc proposing. And then it was explained, in quotation marks, by Uhlenbeck and Gauss-Schmidt, saying that it's related to the rotation, to the spin. But that was very ad hoc. When Dirac wrote his paper in 1928, he explained why there must be spin 1/2. Also, he explained that the electron must have the spin 1/2 electron must have a magnetic moment, which was also known. Experimentally, it was known that the spin comes with a magnetic moment of a certain magnitude. And Dirac not only showed that it must have a magnetic moment, he gave the right magnitude of the moment. And third, he had the correct spin-orbit interaction of the electron, all 3 at once. So it's pure magic that he could do this. It turns out that the spin 1/2 is related to rotation and to group theory. Because SO3 has not only the representations of dimension 1 by 1, 3 by 3, 5 by 5, it also has representations of dimension 2 by 2, 4 by 4. These are called double-valued representations. Double-valued representation is a somewhat more subtle concept than single-valued representation, which I'm sure you will learn from Professor Kenneth Young. But the double-valued representation is deeply related to spin 1/2. For a particle with spin 1/2, a rotation around any axis by 360 degrees changes the phase by a factor of -1. In other words, an object like this, if I rotate it by 360 degrees, it comes back to itself. But a spin 1/2 particle, if you rotate it by 360 degrees, it does not come back to itself. It comes back to itself with a phase factor of -1. This is a conclusion of the double-valued representation. Is that real? Is that something that can be experimentally proven? The answer is yes. In a beautiful experiment in 1975, that fact was proven in an experiment like this. This was a neutron diffraction experiment in which you have a beam of neutron coming in from the left. And this is a single crystal. That single crystal is about this size, in the shape of 3 prongs. And the neutron beam comes in here and split into 2 by the crystal. And then it goes through this path and then recombine at this point. The important thing is that at this point, there is a magnetic field introduced perpendicular to the plane. Now, a magnetic field, because the electron has a spin, so therefore, if this is the electron spin, it's rotating this way, and if this is the axis of rotation, if this is a magnetic field, then the electron spin would precess around it, and this is something that you can easily observe. And so, by putting on the right amount of magnetic field, you can rotate the spin by whatever angle that you want. So what they did was they first had no magnetic field here, and then these two beams would arrive at that point and would reinforce each other because they have the same path. But now you apply a magnetic field on it, then the two beams are no longer at the same phase. And when they rotated by 360 degrees, they found that there's total interference, which shows that exactly a 360-degree rotation of a spin 1/2 particle brings the particle back to the original spinning position, but has changed its phase. So this is a beautiful experiment which showed that double-valued representation of SO3 for spin 1/2 particles is real. In fact, before the experiment was done, in Stony when we discussed this, a graduate student asked me, what would happen if they found that this is not true? If they found that after rotation of 360 degrees, they reimpose each other and not annihilate each other, the two beams. I went back and thought about this, and I came to the conclusion that would be a most important discovery. It would say that the whole of quantum mechanics collapses because there's contradiction in it. And that contradiction is so deep, the whole of quantum mechanics will have to be rewritten. So I said, I don't believe that will be the case. It turns out that, of course, that in fact quantum mechanics triumphed. This is one of the things which showed that the intricacies of group theory not only is just on paper, it is deeply a part of a fundamental structure of the universe. In the 1950s, with several new accelerators, many new particles were found. Their quantum numbers, charge, spin, parity, and quantum numbers due to other symmetries were the main subjects of study. And that led to the famous theta-tau puzzle, which I shall describe to you next time. Everybody is happy? There is sometimes I was asked by students how much group theory they should learn. My advice is the following. For a mathematics student, group theory, of course, is essential, and perhaps every mathematics graduate student should learn a lot of group theory, especially today. Group theory is everywhere in every branch of mathematics. For a physics graduate student, my advice is that you learn as you go along. If you learn too much group theory, you would spend too much time on it, and also much of it is not that useful for physics. But the best way to learn it is when, for example, I've just told you about the fact that because of the double-valued representation, a rotation of 360 degrees comes back for a spin 1/2 particle with a minus sign. And that's related to double-valued representation. So I think that's a chance for you to learn something about double-valued representation. And that's a very beautiful subject. That's how I learned. I can tell you how I learned group theory. First, because I had to write a bachelor's thesis, and Professor Wu Da-you gave me an article called Group Theory and Molecular Physics, which was a fashionable topic in the 1930s. So I read that. It was about the symmetry of molecules. And the symmetry of molecules is a little bit very much similar to what I had talked about of the crystal symmetry. It was a fascinating subject, and it was discrete symmetry. So I learned that because of writing that bachelor's thesis. And then after I went to Chicago, I had to learn more about atomic physics and nuclear physics. Then I had to learn more about SO3. Now SO3 and SO2 are deeply related concepts, and their relationship is related to the double-valuedness. So I had to learn that. And then by the mid-1930s, so I learned a lot about SO3 and SU2, and then SO31 because of Lorentz invariance in Chicago. But after that, in the mid-1930s, in the mid-1950s, it became clear because of all these new SU2s, SU3s, SU5s, and so on and so forth. I and the young physicists of my age all started to learn some group theory. And group theory is a vast subject. What my philosophy was, I learned only those parts that was immediate relevance to what I was working on in physics. But other people have other routes. If you go to younger generation of physicists, because of the fact that the group theory is known to be very powerful, so many theoretical physicists like 't Hooft or the people of his generation learn much more group theory in graduate school than I did. So there's, I guess there's no best way to learn. But if you want to become a theoretical physicist, I think you have to learn quite a bit of group theory. Okay.